Welcome back. Today we're going to look at section 2.6, which involves set operations and compound inequalities. Now, you will have already seen a compound inequalities before, and we will get to them. First, we need to look at set operators. Now, set operators are just relations, just like greater than, less than, that kind of define relationship between sets. The first one is known as the intersection. So if you have a set A and a set B, the intersection, which is defined by this little upside down U right here, is called the intersection and is known as saying A and B. Now, great way to remember, and at least I always remember it, is that the intersection kinda, if you like draw a line through the center of it like this, it looks like an A. So you think of set of A and B. Now what that means is A intersect B, or A and B, is the set of numbers that are in both. In other words, the numbers or elements are in A and they're in B. Now the next operator is called the union operator and is defined by this little U-like thing. And it's known for union, which is easy to see because they both kind of they look very similar. And what this means is or. In other words, it's all elements that are in A or they're in B. They could be in both. They could be just in A. They could be just in B. But what we care about is if it's in one or the other, we're interested. So we're going to look at this with an actual set. So we'll very simple set. We'll just say A. Let's set A be just 1, 2, 3, or 4. We'll let B just be three numbers, 2, 4, and 6. So the intersection of sets A and B, or would be A and B. So what elements are in A and in B? Well, the only elements that are in both of these are 2 and 4. So the answer is this set, which contains only the elements that are in both A and B. Now, if we look at the union, we want numbers that are in A or B. So if it's in 1, we keep it. If it's in B, we keep it. Now, so this means 1, 2, 3, 4, and 6. Now, we do not double count. So in this case, we would not put 1, 2, 2, 3, 4, 4, 6. If an element is in A and B, that you just count it once. You don't need to write 2 twice, because obviously 2 is since we've already listed 2, we don't need to worry about 2 again. Now, when you think about set operators in the 3-part linear inequality that we looked at before, where we were saying x was some number between A and B, well, you could think of that as being an intersection of 2 inequalities. In other words, this is the same as saying we want all x's that are greater than A, and we want all x's that are less than B. It's just another way of saying it. It's not maybe the best way of saying it. This way's obviously best, but sometimes you could be given this and given this, and from that you can go, oh, okay, so we have this, we have the, oh, so that's this one. So it's not really, I'm not looking for, and you shouldn't be thinking of this to this. It's more, you should be able to see this and go, oh, that looks like this. It's kind of a little bit backwards, but that's the way it works. So now we're going to solve and then graph the solution sets. In other words, the answers to, we're going to look at x plus 1 less than or equal to 9 and x minus 2 greater than or equal to 3. So we want only the values of x that satisfy both answers. Well, first thing we need to do is just look at the first one. So we're just going to subtract 1 from both sides, and we get, well, simply x is less than or equal to 8. Now we have to look at the next one, and we get, adding 2 to both sides, we get x is greater than or equal to 5. So what we are looking for is the set of all x's that are less than 8 and x's that are greater than or equal to 5. And the best way to do it is to graph that. So first we graph the first one. X is less than or equal to 8. X is greater than or equal to 5. So we got one going this way and one going the other way. So now our final answer is we're looking at elements that are in both. So every number from below 5 we don't want because it's not here. So we're looking at what's in both. So from here, not here. Okay, you can't look at it. The first number that we come across that's in both is 5. 5 is right here, and it's also right here. So we know it's right here in this set. We can easily see every number right here is in both of them. So we just keep drawing, and then we finally get to 8. 8 is the last number that's in the first set. It is also here in the second set, so we plug it in here, and then we're done. Now what this is just our little try inequality where x is greater than where 5 is less than or equal to x less than or equal to 8. It's all values between 5 and 8. Now we'll look at another one that uses with intersection. Get a little bit more complicated. So now we're looking at all the values of x where negative 3x minus 2 is greater than 5 and 5x minus 1 is less than or equal to negative 21. So again, we just start with the first one. We will add 2 to both sides. We will then divide by negative 3, remembering to flip the sign because we're dividing by a negative. And we get x is less than negative 7/3. Now back to the second one. We add 1 to both sides, cancel that. So we have 5x is less than or equal to negative 20. We're dividing by 5, so we do not flip this. And now we have x is less than or equal to negative 4. So now we just graph our little solution set. So we have first x is less than or equal to negative 7/3, which is negative 2 1/3. So it's not equal to it, so we have an open circle here. And it's every number less than that. Then we know x is less than or equal to negative 4. So from this, it's actually just right here. It's just this one. This one actually simplifies down to, well, x is less than or equal to negative 4 because any number greater than negative 4 is not going to be in both. So we don't even care about any number larger than negative 4. So all this part goes away. So the only thing we're left with is x less than or equal to negative 4. So now, I accidentally gave it away. But in this, we're going to solve the graph to the solution set x plus 2 is less than 5 and x minus 10 greater than negative 2. So as we simplify both sides by subtracting 2 to both sides for the left one, adding 10 to both sides, we're looking for x is less than 3 and x is greater than 12. Well, any number that is less than 3, there's no way it can also be less than 12. As you saw earlier, this is impossible. Therefore, x is empty set. This does look like a 0, and I do tend to write my zeros like this, only because I don't want to confuse it with the letter O. This actually is the symbol for empty set. It means, well, literally nothing. X does not equal anything. And we use that for the empty set, or when X does, there is no solution. There is no solution to this example, so we just say X equals empty set. Now, these next three examples, we're going to go into unions. So now we're going to look at using OR. So we're looking at a solution that solves 6x minus 4 is less than 2x, or negative 3x is less than or equal to negative 9. So what we're looking for will be x's that satisfy one or the other, not both. So first we simplify the first one, moving the 4 to the right side and moving the 2x to the left. So we get 4x is less than 4, or simply x is less than 1. So now, looking on the right, we divide both sides by negative 3. Again, we flip the sign because we're looking at a negative, we're dividing by a negative number. So we just get x is greater than or equal to 3. So now we're looking at x less than 1 or greater than or equal to 3. So this solution is simply this one right here for less than 1. And then we have this one for greater than or equal to 3. So in the case of an OR equation, it's got to be in one or the other, so we just combine both. So every number, so our answer can be here all the way to 1, but it can't be 1. None of these numbers are in either, so we cannot include them. And then we hit 3, and we're into this one. So now we go from 3 and every number greater. So this would be our solution. X is less than 1, or x is greater than or equal to 3. Now we're going to look at another OR equation. This one's a little bit more interesting. So we're going to look at solving the graph of negative 4x plus 1 greater than or equal to 9, or 5x plus 3 is less than or equal to negative 12. So we simplify the left equation, moving the 1 over and then dividing by negative 4, which again, because we divided by negative, we flip the sign. And so we get x is less than or equal to negative 2. Over here, we add 3 to both sides. Subtract 3 from both sides. And then divide by 5. And now we have x is less than or equal to negative 3. So our answer is x is less than or equal to negative 2, or x is less than or equal to negative 3. So in this question, it's very similar to our second example. The biggest difference is we are not taking like the shorter one. It's actually the longer one right here. You see, this one is less than or equal to negative 2, and this one is less than or equal to negative 3. And our answer is just simply this one. X is less than or equal to negative 2, because we only care about if it's in one or the other. So everything between negative 3 and negative 2 works. So we need to make sure we include it. And then, of course, anything less than negative 3 works because it's right here. It just happens to also be in this one. And like I said, we do not double count. We just include. So we don't like draw a second arrow here, like double emphasis or anything. We don't do that. So our solution to this one is just x is less than or equal to negative 2. We're going to finish off with this last example of a union that is going to be even more interesting. It's very similar, and you may already, if you see the pattern we're going with, you may already guess what the answer to this one will be, but let's work ahead anyways. So we're going to look at negative 2x plus 5 greater than or equal to 11, or 4x minus 7 greater than negative 27. So first, we solve the left side by moving the 5 over, and then dividing by negative 2, remembering to flip because it is a negative, and we have x is less than or equal to negative 3. On the right side, we add 7 to both sides, and then we divide by 4 to get x is greater than or equal to negative 5. So we want all values of x that are less than or equal to negative 3, or they're greater than or equal to negative 5. So we draw this, and we get this one for less than or equal to negative 3. We have this number line for greater than or equal to negative 5. And as you can see, every single number is in one of these answers or the other. So our answer is the entire number line. Any real number that we choose, 100, 1000, 42, any number we pick will be in this one or this one. So our answer is the entire number line, negative infinity to infinity and beyond. Again, feel free to click here to see a review of any of these examples that we just went over. If there are any further questions or comments you wish to put, please post here in on the website or in the YouTube channel. Don't forget to look at review question examples, and if you feel stumped on any of them, the answers are in the back. But if you want to know what the steps are, feel free to post on the page in the forums to find out if people are going through the same steps you are. I'll be monitoring and helping out as well. Again, have a great day, and I will see you in class next time.